So we have already talked about events. So events are subsets of the sample space, and since they are subsets, we can do set theoretic, intersection, union, and complements of these events or subsets. So let us work through an example. So say you roll a die. So your sample space is all possible outcomes, which are 1 or 2 or 3 or 4 or 5 or 6. So say you fix an event A as rolling a prime number. So this could be 2, 3 or 5. Or you could roll an odd number, which is the event 1, 3, 5. So you roll either 1 or 3 or 5. Or you could roll an even number. So that is the event is you could roll either 2 or 4 or 6. You could also have an event of just rolling a 4. You could have an event of just rolling a 6. So we have just put down some events from the sample space, and you can see all these events are subsets of the sample space. So let us talk about set theoretic unions. So either A or B, you write it as A union B. It consists of elements either in A or in B. So you have 1, 2, 3 and 5. So you take all elements of A and you take all elements of B, you get 1, 2, 3, 5. Notice that you do not do repetitions. So 3 and 5 are in B, 3 and 5 are also in A, but we just write 3 and 5 once here. So you do not do repetitions. So no repetitions. Now we talk about A intersection B. So you write it as A and B. So it consists of elements belonging to both A and B. So the only elements which belong to both A and B are 3, 5 here, 3, 5 here. So these are the common elements, and that's what you write as intersection. Now we talk about A but not B. So it consists of elements which are in A but not in B. So you write it as A minus B. You also write it as A backslash B. So this is nothing but A intersection B complement. So first of all, let us focus on this part, A minus B. So from A, you take out all the elements of B. So you take 3 out, you take 5 out. So obviously there is also 1 in B, which you do not take out from A because A does not have it. So you just take out the elements which are both common. So that is how you get 2. So you have taken 3 and 5 out of A, which belong to B. Or you can talk about B complement. Now notice what is B complement. B complement is the elements which are in omega minus the B. So that would be this entire omega 1, 2, 3, 4, 5, 6 minus 1, 3, 5. So it's a take out 1, 3 and 5, you get 2, 4 and 6. 2, 4, 6. So A intersection B complement. So this is A, you intersect it with B complement, you just get 2 because 2 is the common element. So this is the meaning of A minus B. Again, notice that you're writing A minus B, but 1 is not contained in A. You're just taking out the elements which are in B from A. Now we talk about mutually exclusive events. So these are also called disjoint events. So you also call mutually exclusive events as disjoint events. So that means there is no common outcome between two events. For example, between B and C, there is no common outcome. It is roll an odd number, 1, 3, 5, roll an even number, C is 2, 4, 6. So B intersection C is just the null set. Again, roll a prime number, A is 2, 3, 5. This intersection with roll a 4, D. So no element is common. So this is a null set again. You can again say, this is the same as this null set will also come if you take A intersection with E. And so on. So now we talk about exhaustive events. So the union of these events makes up the entire sample space. So it makes up the entire sample space. So first focus on this. B union C is omega. So B is 135, C is 246. So take their union, you get 1, 2, 3, 4, 5, 6, the entire sample space. Or you could do A union B, union D, union E. So A union B we have already written right here. So it is 1, 2, 3, 5. So if you add 4 to it, that is D, and you add 6 to it, that is E. So you add 4 and 6 to this. So 1, 2, 3, 4, 5 and 6, you will get the entire sample space omega. So exhaustive events are the ones whose union makes up the entire sample space. Now you can also talk about B and C being mutually exclusive and exhaustive. So B and C are mutually exclusive. These are mutually exclusive and exhaustive. So this is important to notice that you can have events which are mutually exclusive and exhaustive, and this will come up again and again. A standard example is, say you have any event E, then you can find its complement EC. So these are exhaustive because E union E complement is always the entire sample space omega, and they're also mutually exclusive because they do not share any element in common. So E intersection E complement is also the null set. So you can always make up mutually exclusive and exhaustive events. Now we talk about field and sigma field. Now field and sigma field are very important if you want to do higher probability. If you want to do stochastic calculus, you will always encounter terms like sigma field, and you need to understand what this field and sigma field essentially mean. So for field, you start with a sub collection of all events. So you take a sub collection of events. So events are nothing but subsets of sample space. So you take a sub collection of events. Now this sub collection has the following properties. So number one, you can say that if there are two subsets A and B, so A and B are two subsets, or you can say two events, they belong to the sub collection F. So this is curly F is the sub collection. Then the union of these events also belongs to the sub collection. The intersection of these events also belongs to the sub collection. So basically we are trying to collect all events such that their union also belongs to the sub collection, their intersection also belongs to sub collection. That is, union is an event, intersection is an event. So if A belongs to the sub collection, the complement of A also belongs to the sub collection. The entire sample space and the null set also belong to the sub collection. So again, what is a sub collection? So sub collection is nothing but a bunch of events. So you have taken a bunch of events, and these events you call the sub collection, which I'm writing as curly F. The only thing is that these events should satisfy certain properties. The first property they should satisfy is that their union should also be in the sub collection. The intersection should be in the sub collection. The complement should be in the sub collection, and the entire sample space and the null set should also be in the sub collection. So such a collection of events is called a field. So we will see these examples about fields and sigma fields in a bit. So if in addition to these properties, so in addition to these three properties, if you also have that there is a countable union, so there is E1, E2, E3, E4 and so on, or like bunch of events, and you take their union. So union, countable union means that you could go up to infinitely many subsets or events. So you take their countable union, it still belongs to the sub collection, then we call it a sigma field. So notice the difference between field and sigma field is just that there is a sign of infinity here. So if it was just a standard union like this, if you just put n like this here, then this becomes a field itself, because you know you can use this induction, you can take A as, so this you can denote as A, and then B is just En, and I should write Ei here. So that is about field and sigma field. Again, these are very important concepts when we talk about stochastic calculus later on.